Now that we understand the relationship between pressure and volume, we can see how it applies to equilibrium and LCP. As it says at the top here, if the pressure of an equilibrium system is changed by changing the volume of the system, then by LCP, the position of equilibrium will move to change the moles of gas to counteract the change in pressure. And that concept of changing the moles of gas to counteract the change in pressure is an important one, and it links right back to what we learned last year about Avogadro's principle, that equal volumes of gas contain equal number of particles. So for example, if you've got 1 mole of hydrogen gas, which is one of the tiniest molecules of all molecules of gaseous things, and you've got 1 molecule of, say, sulfur hexafluoride, which is one of the biggest molecules of gas, regardless of how big those molecules are, the same number of molecules occupies the same volume. So as long as a reaction can reduce the number of molecules, it can change its volume or change its pressure. And therefore by LCP, if we increase the pressure on a reaction, for example, it will try and shift to reduce the number of molecules, because by reducing the number of molecules, it will reduce the pressure, i.e. counteract our change. And therefore we can go into this next section here. It says, if the pressure of a gaseous equilibrium reaction is increased by decreasing the volume, which means just like the plunger, we squash the volume in and therefore raise the pressure, the side of the reaction with less moles of gas will be favoured, as that will reduce the pressure. So if we squeeze these gas molecules together, if it's an equilibrium reaction, it will try and react in such a way as to reduce the number of molecules and therefore reduce that pressure, i.e. counteract our change. And similarly, if we decrease the pressure by increasing the volume, the side of the reaction with more moles of gas will be favoured, and this will increase the pressure, once again counteract our change. Anything we do, we know LCP says equilibrium will try and counteract our changes. Let's have a quick look at one of the reactions we've already seen. This is the Haber process reaction again, hydrogen and nitrogen reacting to form ammonia. If we look at that reaction now in terms of number of molecules, we see on the reactant side over here, we've got 3 molecules of hydrogen and 1 of nitrogen, which means 4 molecules of gas in the reactants. In the products, we just got our 2 molecules of gas of ammonia. And therefore, let's just say, for example, we increase the pressure on this reaction. We pump it into a smaller vessel, or we decrease the volume of the vessel. So we've increased the pressure. If that's the case, LCP tells us the equilibrium will shift to try and counteract the change, to try and decrease the pressure. And how can it decrease the pressure? Well, if the reaction shifts this way, and some of that hydrogen and nitrogen start reacting to produce more ammonia, that means we're going from 4 molecules down to 2 molecules. Making less molecules, that's how it decreases the pressure. So an increase in pressure should shift the reaction to the right to try and decrease that pressure. And as it says here, via LCP, increasing the pressure, i.e. by decreasing the volume, will shift the equilibrium right, as this will decrease the moles of gas and thus counteract or decrease the pressure change. So let's look at some examples of that. And the first example we've got here is this one here. This is a reaction between hydrogen gas and iodine gas to form 2 molecules of hydrogen iodide. It's endothermic because delta H is positive. Have a think about this reaction. Have a think about these first 2 questions and see what you come up with. Just pause the video and have a think. Okay, this is a bit of a trick question. If we look at the reactant side, we see we've got 2 molecules of gas. If we look at the product side, we see we've also got 2 molecules of gas. And therefore, no matter what this equilibrium does, with whichever way it shifts, it will always end up with 2 molecules of gas on either side. And therefore, this is a bit of a trick question because pressure and volume actually has no effect on this equilibrium. Even though it's a gaseous equilibrium, because the moles of gas are the same on both sides, pressure will not have an effect. So halving the pressure, no effect, as there's the same number of moles of gas on both sides. Halving the volume does increase the pressure, but there's no effect, as we've got the same moles of gas on each side, neither side will be favoured. And that's the same for the next 2 as well. Doubling the volume, that's the same as decreasing the pressure. We've increased the volume, therefore there's more space for the gas molecules to exist in. So that's the same as decreasing the pressure, but that's going to have no effect again, because same number of moles. And similarly, doubling the pressure, we've squashed the molecules close together, but there's no favoured way to react. There's no way whether the reaction reacts this way or whether it reacts that way. It's not going to change the pressure because there's the same moles of gas on both sides, and therefore pressure has no effect. However, cooling will have an effect, okay, because heating and cooling affects all reactions. So have a quick think about what you think that's going to do. Pause the video, write it down, and then check. Okay, and so what's going to happen is, because we've cooled it, that means LCP says it's going to try and heat up the reaction. We know going this way is endothermic, that means it's going to absorb heat. Going back this way, that's our exothermic reaction, that'll release heat. Releasing heat, or heating, is the opposite of cooling, and therefore if we cool this reaction down, equilibrium will shift back to the left because that's exothermic, and that will raise the heat. On to the next example. This is back to our Haber process example for the following reaction. We can also write that, as we said before, as this, because exothermic heat is being produced, but also, as we said before, there's 4 molecules of gas in the reactants and 2 in the products. So have a think about these 5 questions, write your answers down, pause the video, and come back and check your answers in just a second. Well, the first one, halving the pressure. Don't forget that if we halve the pressure, LCP says it's going to try and shift in such a way as to counteract that change. If we halve the pressure, it's going to try and increase the pressure again. How can a reaction increase the pressure? If the reaction reacts this way, we're converting 2 molecules of ammonia into 4 molecules of gas, 3 of hydrogen and 1 of nitrogen. And therefore, shifting to the left actually makes more gas, which will increase the pressure. And so therefore, what Le Chatelier's principle says, or LCP says, is the equilibrium will shift to the left, which makes more moles of gas, to re-establish that pressure again. Halving the volume. Halving the volume is the same as squashing the container, pushing those molecules close together. So halving the volume is the same as increasing the pressure. And now we know it's the same as increasing the pressure. We can say, well, that by LCP, it'll try and shift to the right to make less moles of gas to decrease that pressure. Doubling the volume, that's just making more space for the molecules to move in. That'll clearly decrease the pressure. When you increase the volume, you decrease the pressure. And therefore, by LCP, equilibrium will shift to the left, go back to this way, to make more moles of gas to try and increase that pressure again. Doubling the pressure, we've already seen that situation before. Doubling the pressure, it's going to shift right to make less moles of gas and therefore less pressure. And heating, that means we've added heat. That means LCP says it's going to try and cool the reaction down. How can the reaction cool down? Well, if it shifts towards the endothermic way, it will absorb heat and therefore cool it down. So therefore, by LCP, it'll shift to the left, which is the endothermic reaction, to absorb that heat. We're going to look at one more equilibrium curve this time. So we're going to add a few things to the picture on your notes. We're going to add concentration, going to add time to our x-axis, and we're going to add an extra line called the first equilibrium. We're going to say this section here is where it first starts to go flat. So this little region in here, which I'm going to just highlight here, that's our equilibrium region. The concentrations are staying constant here, and therefore that's our first equilibrium point, which is at that time here. We're not going to go into the full details about how to draw this start bit because it's exactly the same as what we did in situation A3, but this time we're going to be looking at doubling the volume. So situation C, doubling the volume. And just like before, we started off with a whole lot of hydrogen and nitrogen. Some of the nitrogen reacted to produce ammonia, but because it's that 3:1:2 ratio, if we have 1 unit of nitrogen reacting, we'll have 3 units of hydrogen reacting and 2 units of ammonia reacting, but they'll reach an equilibrium, and this particular equilibrium, these are the concentrations of those 3 gases at that particular equilibrium. But we're going to do something now. We're going to double the volume. And don't forget, increasing the volume is the same as decreasing the pressure, and that's going to be very important to analyse this situation. So at this time, at this new line here, the volume's been doubled, and thus the pressure has been halved, or in other words, has been decreased. Now, as far as concentration is concerned, with gases, we don't usually measure their concentration in moles per litre, we measure it in terms of pressure. So effectively, if we have halved the pressure, we've effectively halved the concentration of each of those gases. So if we halve these concentrations, what that means is each of these 3 gases at these concentrations drops to half their current value. So for nitrogen, for example, it's dropped down here to half its current value. Let's put a dot there to remind me it's dropped to half its current value. For hydrogen, it's dropped down to half its current value, which I've estimated to be about there. For ammonia, it's going to drop down to half its current value, which I've estimated to be about there. So those 3 dots represent the half values. And all I do now is recognize that this was a very quick or very sudden pressure change. So these things have dropped very quickly. So nitrogen's dropped to there very quickly, hydrogen's dropped to there, and ammonia's dropped to there very, very quickly. Now we've changed the conditions of equilibrium, which by LCP tells us something's going to change. The situation is going to try and readjust to counteract that change. And we already know that by doubling the volume, we've decreased the pressure. Therefore, it's going to shift to the left to make more moles of gas. And that means the reaction is going to go this way, which means we're going to make more hydrogen. We're actually going to make less ammonia. So thinking about that, I know the nitrogen is going to go up. I'm going to say, I'm just going to choose some arbitrary point. This is my point where the next equilibrium is going to be reached. And I know that nitrogen is going to go up, so I was going to say, well, nitrogen is going to go up by 1 unit. I'm going to put a dot there to remind me that's where nitrogen is going to finish. I know hydrogen has to go up by 3 times as much, so there's my times 3 times as much hydrogen going up, once again, because it's that 3:1 ratio. If 1 unit of nitrogen is produced, 3 units of hydrogen have to be produced. And by the same token, ammonia has to go down, so it's gone down by 2 units worth. So I'll put those dots there to remind me where those reactions have to finish, and I'll just draw my lines on. Nitrogen increases at that point and then reaches its equilibrium, its steady concentration. Hydrogen increases at that point, then its concentration stays steady, because once again it's reached equilibrium, its concentration won't change, and ammonia decreases at that point, and then it stays steady, because once at equilibrium, its concentration doesn't change. A new equilibrium has been established. What that means is, we've reached equilibrium, these concentrations are no longer changing, because once again the rate of forward reaction equals the rate of reverse reaction, but look at the concentrations. Equilibrium used to be with these concentrations, equilibrium is now with these concentrations. That's what that means, that we've reached a new equilibrium once we've changed the conditions. Let's look at the third example, B3, the following reaction. 2 carbon monoxide gas molecules in equilibrium with carbon dioxide gas and carbon soot. It's still a H negative, which means it's exothermic, so we can write that as plus heat in our product side. I'm going to recommend you have a go at these 5. Pause the video, have a go, and then check your answers in a minute. Going through them, what you should have realised is that there was 2 moles of gas in the reactants and 1 mole of gas in the products. Carbon soot is not a gas, and therefore it doesn't actually influence the volume and pressure changes. It's only these 2 things that are influenced by volume and pressure changes. Knowing that, if we look at what's happening when we halve the pressure, if we halve the pressure, it's going to try and shift to the left to make more moles of gas to increase the pressure again. If we halve the volume, that's the same as increasing the pressure because we squash the molecules together. Therefore, it's going to shift to the right to try and make less moles of gas to decrease the pressure. If we double the volume, that's the same as decreasing the pressure because we made more space for the molecules to exist in. Therefore, it's going to shift to the left to try and make more moles of gas to re-establish that high pressure. If we double the pressure, it's going to shift to the right to try and decrease the pressure by making less moles of gas. And if we cool, it's going to try and do the opposite of cooling, which is heating. Therefore, the exothermic reaction is favoured, and therefore it's going to shift to the right because that will increase the heat. We're not going to draw the graph now. We're going to draw more graphs when we do chemical monitoring and management. So that leads on to the third thing that can affect equilibrium. We've seen temperature, we've seen pressure and volume, which are linked together. The third thing is concentration, and this is for systems involving a solution or a gas phase, because they're the things that can change concentration. A solution, we know we can change the concentration of a solution by changing the moles per litre dissolved in the solution. For a gas, we've just seen we can change concentration by changing the pressure of a gas. So what does LCP say? LCP says if the concentration of a species in an equilibrium system is changed, by LCP, the position of equilibrium will move to counteract the change in concentration of that species. I actually think this is the easiest one to analyse, which is good we left it last, so it's nice and easy to finish with. Because all that happens is if you increase the concentration of a species, such as you add more chemical to a solution or you increase the pressure of a gas by pumping more in, all that happens according to LCP is that the equilibrium will shift to react and consume that species. Whatever you add, it'll try and consume that species. And similarly, if you take a chemical out of solution or you decrease the concentration of something, all that's going to happen is that equilibrium will shift to try and make more of that chemical you've just taken out. Once again, LCP says the equilibrium will try and counteract whatever you do to the system. So what does changing concentration mean? As we said a second ago, first of all, changing concentration can just mean changing the concentration in moles per litre of a chemical in solution. The other thing you can do to change concentration is to change what's called the partial pressure of a single gaseous species, which could just mean pumping more of that particular gas in or out of a reaction. So in our Haber process reaction, if you pumped in more nitrogen, you'd be increasing the partial pressure or the concentration of that nitrogen in that gaseous reaction. This is a good time to note there are some things that don't affect equilibrium though. We've just studied the 3 things that can affect equilibrium, which is temperature, pressure, i.e. volume, and also concentration, but there are 3 things that, while they might affect rates of reaction, they don't actually change the position of equilibrium, they don't change those concentrations at equilibrium. And the first one of those things is adding in or pumping in an inert gas. Now this can be a bit confusing at first because you might think of pumping in a gas, you're actually increasing the pressure. We've talked about how pressure changes affect equilibrium, but it doesn't actually increase the partial pressure or the concentration of any particular gas. Because the pressure is put on all the reacting gases at the same time, it doesn't affect the relative proportion of any reacting gas. Or it says here, this increases the pressure of the container, but doesn't affect the partial pressure of the gases, and that doesn't affect equilibrium. The way I used to think about this was I'd imagine that inert gases being pumped in, not only are they pushing the gas molecules closer together, but they're also getting in the way, getting in between the gas molecules, and therefore it sort of counteracts the effect and therefore has no effect overall on the equilibrium. That's not something you'd actually write down, just a way to think about it. The next thing that doesn't affect the position of equilibrium is changing the amount of a solid reactant. If you add more solid, you might make the reaction happen faster because you're adding more reactant. If you, so for example, increase the surface area, the rate of reaction might increase, but it won't actually change the position of equilibrium, the amount of chemicals you have and what concentrations they have at that equilibrium point. And the third thing that doesn't change position of equilibrium is adding a catalyst. Once again, adding a catalyst can increase the rate of reaction. It can make you reach equilibrium faster, but it won't actually change the concentrations of those species at equilibrium. We're going to study these three things a bit more when we look at the Haber process and chemical monitoring management, but it is important now you know that these three things don't affect the position of equilibrium. They don't apply to Le Chatelet's principle. Let's look at some examples of changing concentration. So example C1, for the final equilibrium, what would be the result of doing the following things? And once again, it's just the Haber process equilibrium. Therefore, we can write that down with plus heat because it's producing heat. We can pretend heat is like a product in this reaction. So what happens if we double the nitrogen? We've actually increased the amount of nitrogen. Well, LCP tells us that whatever we do, the equilibrium is going to try and counteract that change. If we've just increased the nitrogen, it's going to try and shift the equilibrium to use up or consume that nitrogen. And therefore, all that happens is, by the LCP, the reaction is just going to shift to the right. If we've increased the nitrogen, it's going to try and convert that nitrogen to ammonia to use up that nitrogen. If we halve the amount of ammonia, we've just dropped the amount of ammonia, all that's going to happen is it's going to shift to the right to replace that ammonia. If we take away ammonia, hydrogen and nitrogen are going to react more to replace the ammonia we take away. If we halve the amount of hydrogen, if we take away some hydrogen, all that's going to happen is ammonia molecules now are going to start decomposing to try and replace that hydrogen. So if we halve the hydrogen, it's going to shift to the left to increase the amount of hydrogen. I'm going to do one more of these diagrams. I think this is our last diagram we're going to draw this style in this particular focus area. We're going to focus on the one doubling the nitrogen. So it's situation A in set C1. At the start, it's exactly the same as what we did for A3 and B2. We start with hydrogen and nitrogen. They drop in the ratio 3 to 1. We start with no ammonia. It rises up as 2 times the amount of nitrogen that's being produced. It reaches the first equilibrium, and we're going to make some sort of change at this point after it's at equilibrium already. And what that change is, we're going to double the nitrogen concentration. And this could be like pumping more nitrogen into the actual reaction vessel. Now, because we're only pumping nitrogen, it's only the nitrogen partial pressure, only the nitrogen concentration that doubles. And all we've got to do is, from this initial value here, we just double the concentration of nitrogen because that's what the question says. From that point on, we already know what's going to happen. We said that it's going to shift to the right to decrease the amount of nitrogen. So similar to before, I've drawn that line on showing that there was a very rapid increase in the nitrogen concentration to double value. And then I make some arbitrary point, equilibrium is going to reach here. And then I start putting my dots on. I say that, okay, ammonia is going to decrease. I'm just going to say it's going to decrease by that much. That's 1 unit. Hydrogen is going to decrease by 3 times as much. So there's 3 times that much. That's my hydrogen decrease. And ammonia is going to increase by 2 times that much. And there's my 2 times that much increase. I'll put my dots on. All that's left now is to put those curves on. There's the nitrogen curve. It drops to a new equilibrium. We've got the hydrogen curve. It drops to a new equilibrium. And the ammonia curve, it increases to a new equilibrium. And once again, I've reached this position where the concentrations are no longer changing. That means the rates of forward reaction and reverse reaction are the same. It's reached an equilibrium, but it's a different equilibrium to what it was before. And that's what the LCP says. It says if you change the conditions, in this case increase in the nitrogen, the equilibrium will shift and a new equilibrium, which means different concentrations of equilibrium reactants and products will be established. There are some more examples in set C though. Let's have a look at these. This one here is a reaction between solid carbon and water to produce carbon monoxide and hydrogen gas, and it's exothermic, as it says here, delta H is negative. So we can write that like this. Have a go at these, 9 different sets. The answers will appear on the screen in a second. You can check them yourselves, but there are a couple of tricks which I'll talk about in just a second. So pause this now, have a go, and just check your answers in a minute. I'm not going to go over all these answers, so it'd be a good idea to pause them and just double check all your answers. If you got something wrong, can you figure out why it was wrong? If you can't, please come and ask me. The real trick was this one here, B, adding more carbon. If you weren't being very careful, you're trying to think too quickly, you've just studied that adding a particular reactant, the equilibrium will shift to try and consume that reactant, and that's true, except in the case of solid reactants. Increasing the amount of solid doesn't affect the position of equilibrium, so you're very aware of that. Adding more carbon, it might make the reaction go faster, but it won't affect the position of equilibrium. It won't affect the concentration of those species at equilibrium. The third example for effect of concentration is example C3, and this is the carbon dioxide and water equilibrium that occurs in soft drink, which we'll study in a bit of detail in experiment 10. It's a double equilibrium, so for example, carbon dioxide and water react to produce carbonic acid, but carbonic acid actually decomposes to produce hydrogen ions and bicarbonate ions. Because it's an acid, it produces hydrogen ions. It's exothermic, and therefore every reaction that way is exothermic in this particular case. and you've been asked to analyse the effect of these 7 things. So once again, pause the video, have a go at those 7 things, and then press play and see the answers and check the answers. Once again, I'm not going to go over all these answers, so please pause the video and check your answers in turn. If you have trouble with anything, please let me know. But some of the key things here was to recognise that carbon dioxide is the only gas in this reaction, and therefore anything to do with pressure or volume will really only affect the carbon dioxide, so you can focus on that one thing. So look at increasing the pressure. If we increase the pressure, it's going to try and decrease the pressure by making less moles of gas, therefore it wants to make less carbon dioxide, therefore it shifts to the right. Adding acid, we know that acids add hydrogen ions to aqueous solutions, and therefore when it says adding acid, that's key for saying really I've increased the hydrogen ions, therefore it's going to shift back to the left to try and remove those hydrogen ions. Adding sodium bicarbonate, there's no sodium in this equilibrium, but there is bicarbonates. Adding sodium bicarbonate, adding both sodium ions and bicarbonate ions, the sodium ions don't do anything, but the bicarbonate ions, by increasing them, I'm going to shift the equilibrium back to the left to try and consume them. Adding a base is the same as actually decreasing the hydrogen ions, because I'm taking hydrogen ions away, and therefore it's going to shift the reaction to the right to try and replace those hydrogen ions, and the rest are pretty straightforward, stuff we studied before. Once again, if you're not sure about something, please ask. We've looked at the 3 things that can affect equilibrium position in LCP now. Now we're going to look at 3 case studies: indicators, the bromine water experiment to test for alkenes, and also weak acids to see how LCP applies to those 3 situations. Now, indicators is something we have studied. We know they're a solution or an aqueous mixture of chemicals in equilibrium, and that hydrogen ions, this is something you might not know, hydrogen ions are part of that equilibrium. And because it's an equilibrium and LCP applies, that means any time the concentration of hydrogen ions is changed, for example by adding an acid or base, the equilibrium of the indicator mixture actually shifts. Now don't forget, this is an important point, that adding acid raises hydrogen ions, adding a base lowers hydrogen ion concentration. And it's also important to note that chemicals in equilibrium indicator are actually quite complex. We can actually simplify it down. Now this equation in the box is the one we're going to be focusing on. At its simplest form, an indicator consists of a chemical, in this case HX, which is an equilibrium with hydrogen ions and a chemical called X-. And it's clear that X- plus hydrogen ions will reform that chemical HX. What's really happening though in terms of Bronsted-Lowry theory is the actual fact that indicators are actually mixtures of weak acid and its weak conjugate base. So for example, chemical HX is a weak acid. It will donate protons to the water, and in doing so it turns into its conjugate base. Here is X-. This is the weak conjugate base, sorry about the poor writing, and this is just a weak acid over here, and hydronium ions are in there as well. So essentially an indicator is a mix of a weak acid and its weak conjugate base. But what's critical about this compared to most mixtures of weak acid and weak conjugate base is that indicators are chosen so that species have different colours. So chemical HX, which in this case was the weak acid, is purple, and the chemical X-, the weak conjugate base, is green. So these solutions, these indicator solutions, are always chosen so that either side of the equilibrium there is a different coloured chemical, and that's how it changes colour when you add acid and base, as we'll see down here. So for example, if you add an acid to the indicator, that's the same as increasing that hydrogen ion concentration. Now by LCP, that means equilibrium is going to shift. It's going to try and shift to counteract the change. And what does that mean to counteract the change? Well, if I've increased the hydrogen ions, it's going to try and shift to the left. Okay? And why is it going to try and shift to the left? Because by shifting to the left, that means the hydrogen ions and X- are reacting together. That means taking away those hydrogen ions, producing more HX, because that decreases the hydrogen ion concentration again. If I've increased the hydrogen ion concentration, LCP says it's going to try and decrease that hydrogen ion concentration. And what's the effect of that? Well, if the equilibrium shifts to the left, that's going to make more chemical HX. That's going to make the indicator appear more purple. So adding acid to this indicator makes it change purple. However, if I add a base, that's the same as lowering that hydrogen ion concentration. So by LCP, that says it's going to shift to the right. Why is it going to shift to the right? Because by shifting to the right and HX decomposing, it's going to make more hydrogen ions to replace those ones which I've taken away. If it shifts to the right, I'm decomposing this purple chemical and making more of this green chemical. So for this indicator, if I add a base, it's going to turn green. And that's the basis of how all indicators work. Because they're in equilibrium which contains hydrogen ions, and either side of the equilibrium contains a different coloured chemical, if you add or take away hydrogen ions, it's going to shift the equilibrium one way or the other, and therefore change the colour of that chemical, and therefore you can tell the pH of something based on its colour. The next thing we're going to look at is the bromine water test for alkenes and how it relates to LCP. Now I just want to make it very clear, you don't need to go into this detail of the LCP and what's going on if you're answering a question on the brine water experiment. This is purely for information to see how LCP applies in a range of situations. So we previously said that brine water was just this simple thing. Oh, it doesn't look like brine water there. So we usually said it was Br2 aqueous, and that's all we said brine water was. But in actual fact, it's actually a bit more complicated than that. Br2 aqueous doesn't exist on its own. Br2 aqueous actually reacts with water, and in the process of reacting with water, it reacts in an equilibrium reaction to produce these two chemicals, hyperbromous acid and hydrobromic acid. And even though in the past we said it was this Br2 molecule, this brown Br2 molecule that reacted with the alkene, it's actually this thing, the HOBr. That's actually really what reacts with the alkene. So what it does, it undergoes an addition reaction, just like most alkenes do. So here's our hex 1N, our alkene. It reacts with this HOBr, the hyperbromous acid. The hydroxyl group bonds with the first carbon. The bromine bonds with the second carbon. So it bonds across that double bond in a typical addition reaction to produce 2-bromohexanol. Now, once again, you don't need to write this down in your HSC responses, it's just for your information. But a question you might be asking is, well, if we're just reacting a clear chemical and we're just taking away one of the clear chemicals, why does that make the brine water turn clear? Well, the answer is because this reaction goes to completion. And that means that any time there's any HOBr in solution and any hexene in solution, they will immediately react together and that will form this chemical, and that won't form back into HOBr again. It's not equilibrium. And that means that every time this reaction takes place, the HOBr concentration drops. And that means we're affecting this equilibrium reaction up here. So because we're removing the HOBr, LCP says this equilibrium is going to shift to the right to try and replace that HOBr. Okay, so it's going to shift to the right to replace the HOBr, but as this equilibrium shifts to the right, what that means is we're consuming this brown Br2 molecule. And as long as there's hex 1N in solution, which constantly takes away the HOBr, this equilibrium will keep shifting to the right, shifting to the right, shifting to the right, constantly consuming the Br2. So this consumes the brown Br2, and as long as there's an alkene consuming the HOBr, the equilibrium will continue to shift to the right until all the Br is consumed, which means it turns clear in the presence of an alkene. The last example, which is probably not in your booklets, but it's an important one, is the effect of dilution on weak acids. Now we know already that weak acids exist in equilibrium with water, and the weak acid exists in equilibrium with its weak conjugate base. We know that the weak acid donates a proton to the water, etc., and that also the reverse reaction occurs. If you dilute a weak acid though, which means you're diluting this whole equilibrium, because the whole equilibrium exists in the water, you don't just have weak acid in the water, you have this whole equilibrium in the water. If you dilute it, you lower the concentration of the weak acid, but you're actually lowering the concentration of two products. And that means on dilution, LCP says the equilibrium will actually try and shift to the right to raise the concentration again of those two products. Because the equilibrium is shifting to the right, that means in actual fact a greater percentage or more weak acid molecules are ionizing. And that means that as you dilute a weak acid, it actually becomes stronger because more or a greater percentage become ionized. It doesn't mean it becomes strong, it doesn't mean it becomes 100% ionized, it just means that more percentage molecules ionize, and therefore technically weak acids become stronger when they are diluted. That's an important point. Please make note of that. It has popped up in the last couple of HSC papers. And moving on to the last example we're going to look at in our LCP section. This is the solubility of carbon dioxide in water. Now, this is a very important reaction. It's important for your body to perform. It's important for respiration. It's important for photosynthesis. It's important for removal of carbon dioxide from the atmosphere. It's important for ocean acidification and the greenhouse effect. And it's important in preparation of soft drinks, which is the most important application we study in the HSC course. Carbon dioxide is interesting in the fact that it's so soluble in water. The CO2 molecule, one carbon double bonded to two oxygens either side, is actually a non-polar molecule. It's a non-polar covalent molecular molecule, and therefore it should not dissolve readily in the very polar water molecule. But it does dissolve very readily. It's actually much more soluble than most atmospheric gases, and the reason it's so soluble is because it reacts with water. It actually undergoes a reaction to produce carbonic acid. But the reaction is an equilibrium reaction, and therefore everything that can affect that equilibrium, temperature, pressure, concentration, will affect the rate at which carbon dioxide dissolves. For instance, anything that makes equilibrium go this way, we say that increases the solubility of carbon dioxide. Anything that makes the equilibrium go that way, which means the carbon dioxide comes out of the water, makes carbon dioxide less soluble. So let's look at some of those things. First of all, if we somehow decrease the amount of carbon dioxide in the atmosphere, and obviously we can't do it for the Earth's atmosphere, we might be talking about the atmosphere in a container or a jar or a reaction vessel, anything that drops that carbon dioxide concentration will shift equilibrium back this way to replace that carbon dioxide. So therefore, decreasing carbon dioxide concentration actually makes carbon dioxide less soluble. However, if we do manage to increase carbon dioxide concentration by pumping carbon dioxide into a system, that'll shift the reaction back that way, according to LCP, making the carbon dioxide more soluble. If we add acid, it'll drive the reaction back to the left. If we remove acid, it will drive it to the right. If we increase the temperature, this being an exothermic reaction, it will favour the endothermic reaction and drive it back to the left. So all the things we've been studying so far, temperature, pressure, concentration, all those things will affect this particular equilibrium. And how we study that is mainly in experiment 10 when we look at soft drink. Soft drink equilibrium. This is exactly the same reaction as before, this little bit just here, this red bit or this black bit at the top. It is a little bit more complicated because the carbonic acid itself is in equilibrium with carbonate ions, so it's with bicarbonate ions, hydrogen ions, which are in equilibrium with carbonate ions and more hydrogen ions. So it's quite a complex series of equilibriums. I've got them here written just as normal, but you should be aware that Bronsted-Lowry theory applies everywhere. Carbonic acid being an acid, yes, we can say H2CO3 is in equilibrium with bicarbonate ions and hydrogen ions. What's really happening though, it itself is reacting with water to produce the bicarbonate ions and hydronium ions, and similarly bicarbonate ions can react with water to produce carbonate ions and hydronium ions. Just be aware that anytime we have free hydrogen ions in any equilibrium system, we probably should put the H3O plus in there. So what does that mean for soft drink? Well, let's have a look. We know that temperature, pressure and concentration all affect position of equilibrium by LCP. We've said previously that anything that makes this reaction go that way, that's the same as increasing the carbon dioxide solubility. That means more carbon dioxide is being dissolved into the water. Anything that makes the reaction go back that way, that's decreasing our carbon dioxide solubility, because carbon dioxide, when the reaction goes that way, will start bubbling out of the solution. So let's think about what happens to your soft drinks. If you leave your soft drink somewhere where it's very hot, you'll probably notice it goes flat very quickly. And why is that? Well, this is an exothermic reaction. If we raise the temperature, the equilibrium is going to try and shift to favour the endothermic reaction. And we know the endothermic reaction is going back this way. Therefore, if we heat up soft drink, it's going to drive that equilibrium backwards. Therefore, the carbonic acid is going to decompose and turn to carbon dioxide. That means that carbon dioxide is going to bubble out of our drink. The fact that carbon dioxide is bubbling out of the drink means that the carbon dioxide is less soluble. It's bubbling out because it's less soluble. And therefore, you keep your soft drink in the fridge, because if you heat up your soft drink, it's going to go flat because you're driving the carbon dioxide out. Similarly, you know that if you open a bottle of soft drink and leave it open, it becomes less fizzy over time, it becomes flat over time. That's because if you open the bottle, you've actually decreased the pressure inside that bottle. Decreasing pressure, well, that just means the equilibrium wants to try and increase the pressure again. How can you increase pressure? By making more gas. If you open the bottle, it's going to try and shift the equilibrium back this way. The carbon dioxide is going to bubble out of solution to try and raise that pressure, and therefore soft drink goes flat, i.e. carbon dioxide becomes more soluble when the can is open because you've decreased the pressure. So anytime equilibrium shifts left, we say that's the carbon dioxide being less soluble, the carbon dioxide bubbles out of the drink, and that means the drink is going flat. So 2 examples, we've just had a quick explanation of that. Here's your chance to pause the video and try and answer these questions. But it's very important. If you're ever talking about an equilibrium reaction in any extended response, you must refer to the actual reaction. Write the reaction down and refer to the reaction. In addition, you must refer to LCP in your answer, because that's what this whole set of notes is about. Have a go at both these answers. We'll look at some answers in just a second. Okay, for the first one, you might not have these exact words, but you need the sentiment. First of all, I've said, as shown in the equation, I've referred to the equation. Carbon dioxide dissolving water is exothermic, as it says here, it's until H negative. By LCP, so there I am referring to LCP, when the equilibrium is heated, the position of equilibrium will shift to the left, favouring the endothermic reaction to absorb the heat. Thus, on heating, carbon dioxide becomes less soluble and hot soft drink goes flat. So I've answered the question as best as I can. The next one. When half the bottle is empty, the volume of air above the liquid increases, and thus the pressure of carbon dioxide above the liquid decreases. So I've talked about decreasing the pressure. By LCP, now referring to LCP, the position of equilibrium will shift to the left to raise the carbon dioxide pressure. Thus, after opening, the CO2 becomes less soluble and the soft drink goes flat. Just be very careful. I've mentioned going to the left. I only allowed to do that because I've got the equation on the page. Without an equation saying left or right means nothing. But in this answer, I've referred to the pressure, I've referred to LCP, I've said the consequences, and I've answered the question, why does it go flat? Make sure you've done the same in your answers. And that takes us to the end of this section on LCP. There are a lot of examples in your booklet, so I'm going to put a little note here, do the examples. They're all very important in your booklet. But all that's left now for this focus area 2 is the acid rain research you need to do for your holiday work. Gas moles revision, we've done a lot of this in year 11, we're going to revise it again, we're doing experiment 10, and to actually do the experiment 10 as part of our coursework. Thank you for listening.